So as we look at today, we are continuing the information that we previously have done with vectors. What we're looking at today, if you look at the top, is the dot product of vectors. And so when you look at the information here, the dot product or inner product of two vectors is found by, and if you look on the right-hand side of what I'm boxing in right here, that's the most important part. So the way that you go about doing it is you multiply your horizontal components, multiply your vertical components, and you add them together. So if you take a look at number 1, you're going to multiply the horizontal components, so 3 and 5, and then you're going to multiply your vertical components of 4 and 2, and you're going to add those two together. So 3 and 5 will give you 15, 4 and 2 gives you 8, so the dot product of those two vectors is 23. If you look down below, number 2, same concept. We're going to multiply our horizontal components. We're going to multiply our vertical components. And then we add them together. So you have -4 plus -6, which gets you a dot product of -10. So if you look over on the right-hand side is the exact same thing, just written in a different form. So keep in mind that what you're looking for is your coefficients here. So here is the horizontal component. You have a 2 and a 3 as the coefficients, and then you're looking at your vertical components of -1 and -5. So again, make sure, pay attention to those negatives. We're going to do the product and add those together. So 2 and 3 gives you 6, -1 and -5 gets you a +5, so your dot product is +11. If you take a look at number 2, I'm going to let you try out the second one, but just be mindful that this, since it only has one thing written down there, you don't have an I value. So in other words, it's a 0I and then -3j. That is the equivalent to that -3j in that second piece. So take a minute, figure out your dot product of that second thing. All right, now one of the things to be thinking about is think about why. Like, why are we doing this? And the key is that we can use the dot product to find the angle between non-zero vectors. And so what that means is you can do the cosine of an angle is going to be equal to the dot product divided by the product of the magnitudes. So we've done magnitudes before, we'll do a little review of that. But keep in mind, once you do this right-hand side, to find the angle itself, you'll have to do the inverse cosine of that right-hand side to be able to find the angle itself. Okay? So we're going to do a practice with this. What I want to encourage you is just to break it down. So on that previous screen, we did the dot product. So start there. So you've got the product of the horizontals is 2 and -2. The product of the verticals is 3 and 5 together. And so you would end up with -4 plus 15, which gives you a dot product of 11. The second thing that we want to consider is our magnitudes. So if we take a look at our magnitudes, keep in mind that this indicates the horizontal and vertical movement of that vector. So we can go ahead and just do 2 squared, that's our horizontal, 3 squared, that's our vertical, and do the square root of that. So you get 4 and 9 on the inside, which gets us the square root of 13. If we took a look at the dot, or excuse me, not the dot product, the magnitude of V, again, we've got the horizontal and vertical component already given to us. We don't have to do any work for that. So -2 squared plus 5 squared, which I'm going to just cut out the middleman here of the work in between those steps to get the square root of 29. So what you would do is then you would recognize that you're going to do the cosine of theta is equal to the 11, the dot product, over the product of those two magnitudes. Okay, and this is going to give you a gross decimal. That's fine. And what you would do then is you would do the inverse cosine of that number, that whole thing. Okay, so take a minute, see what you come up with for that. Hopefully you came up with 55.5 degrees for that angle measure. Okay, so what that means, let's take a look at a picture just to kind of reinforce this. One second. There we go. This is what I want. So what that means is that if we were to take a look at those two vectors, so 2 to 3, so we're going to go over 2 units, up 3 units. And then from that same point, we could go down, or left 2, up 5. So left 2, and then up 1, 2, 3, 4, 5. That angle formed by those two vectors is going to be 55 degrees. Okay, so when you take a look at this, you could then use that same concept to look at the second one. So let me delete these out of here real quick for us. Move this over here for just a second. And we can go ahead and we can figure out your dot product of u and v. So again, horizontal components are 2 and -3. So we're going to multiply those two together. Vertical component. So -2, -3. So we end up with -6 plus a +6, which gives us 0. Now, before we keep going and do the magnitudes of things, I want you to think ahead. If we do the inverse cosine of 0 divided by anything, okay, or think about your unit circle, okay, your cosine of being 0 means that it's going to be here on your unit circle, which means that's been a 90-degree angle. So anytime that you have 0 in the numerator, even if this could be any number on the bottom, that tells you that your angle measure is 90 degrees. Okay, so let's take a look at what that means in terms of our picture. So again, keep in mind these vectors are not ordered pairs, so we can start anywhere in our graph. So I could even start at 0, and I could go over 2, down 2, and that's my first vector. And then I could go left 3, down 3, so left 3, down 3, and sure enough, that angle formed by those is a 90-degree angle. So the last thing that we want to look at is we want to look and see if the vectors are orthogonal. Okay, so notice here, it's saying if your dot product is 0, that means they're orthogonal. If you take a look at our previous example, we had a dot product of 0. That means those two vectors, u and v, are orthogonal. And what that means is that your vectors are perpendicular. So I'm just going to put here kind of little bubble. So graphically, the vectors would be perpendicular. Okay, form a 90-degree angle. So if you take a look at this, you've got the dot product, u, v. So again, horizontal components, 2 and -6. Vertical components, 3 and 4. We add those two together, you get -12 plus 12, which is 0. Therefore, it checks that those are indeed orthogonal. Now, if you think back to what you guys already know about perpendicular, you could, so from previous knowledge, you could check your slopes. Okay, you don't have to. What we just did in red proves that they're orthogonal. But if you think about your slope, okay, it's rise over run. So if we look at the slope of vector u, rise over run, so 3 over 2, the slope of v, again, we're looking here now, rise over run, simplifies to be 2 over -3. These are opposite reciprocals. And if you think all the way back to algebra, if you have slopes that are opposite reciprocals, those lines themselves, or in this case, our vectors, are indeed perpendicular. Okay? So the dot product allows for you to figure out the angles between vectors. It also allows for you to check whether or not those vectors themselves are orthogonal. Okay? Hopefully that all makes sense. Let me know if you have any questions. Thanks.